Hello everybody, I'm Martin Jutzeler and I'm going to talk about the hazards linked to the 2019 pumice raft in the Southwest Pacific. Before talking about hazards linked to those pumice rafts, I want to introduce the concept of what is pumice and what are pumice rafts. So pumice are the product of silicic volcanic eruptions, and when those eruptions occur underwater, they're going to create these mats of pumice that are accumulated on a tight area in the ocean, and they're going to be transported and dispersed by ocean currents and winds up to 10-30 kilometers per day. Those pumice are a few millimeters to meters in size in some rafts, and those rafts can be dispersed for weeks to years. So pumice raft is one hazard from submarine volcanism. The major hazards would be tsunami, where we have cavitation or sediment flows or landslide that occur during or after the volcanic eruption. That would be the major hazards from submarine volcanism. Another hazard that would occur very close to the vent would be direct hit by a volcanic jet or a rising magmatic gas bubble that can engulf a vessel. So the hazards from pumice raft are mostly linked to inoperability of the marine radars, where boats cannot be discerned from a pumice raft when it crosses it, or that the water intake systems get clogged by pumice and thus you lose the power on the ship. Pumice raft can also block harbors and maritime routes, and considering that 90% of the world trade is done by boat, this can derive to major consequences worldwide. There's also other hazards like spoiling beaches to tourism that are more minor hazards, or the destruction of coastal habitats by blocking the sun, directly blocking the sunlight to the organisms living underneath. So in 2019, in August, we had a pumice raft that was emitted in the Tonga, on the Tonga Kermadec arc. And so we have the volcano here to the top right of the image, and we're going to look at the dispersal of this pumice raft from this place here in the Tonga Island to the Fiji Islands in this area. So this eruption occurred at an unnamed caldera volcano that is entirely submarine, but the vent is very shallow at 200-meter water depth. It's centered on a massive 8 by 5 kilometer caldera, and this vent is actually very similar or very close to the 2001 eruption that also emitted a pumice raft. A best way to identify and monitor a pumice raft is to look at satellite images. So we have moderate resolution images that are 200 to 300 meter per pixel, but they are bringing new images every day, so it's extremely powerful for tracking a raft. We also have high resolution satellite images that go to less than a meter to 30 meters per pixel, and those are very useful to understand the dispersal of the small rafts. We also have the possibility to have radar images of those rafts at 10 meters per pixel, and that's extremely useful in case of bad weather, because the clouds are usually obstructing the rafts. So we have the opportunity to get for free almost real-time images that allow us to identify where the raft is going and where it's traveling. We also have, in this case, in 2019, we have several sailing boats that crossed the raft, and that was a really good opportunity to talk to those sailors to understand a bit more the behavior of the raft, but also to get samples and to understand that the raft was mainly thin, but up to 30 centimeters thick in some places. And the clasts were millimeters in size to up to 80 centimeters in diameter. And on the map, you see this satellite image, the summary of the satellite images in rainbow colors, from the red here on the 9th of August to the teal colors in the 17th of August, and you see the dispersal of this raft through time every day. But in a dashed black line, you have where those boats cross the raft. Eventually, pumice rafts will reach some islands and get stranded there. And depending on the winds, they can stay up to a few days to up to 2 months in the case of the Yazawa Islands, where we have the vision here of a small motorboat that is stranded here, and the open ocean that is just barely visible in here. In the Lakeba Island, we have this little fishing village here that is totally blocked from the open sea by this raft in grey-brown. So combined data, we have a raft that was about 30 million cubic meters, and at day 2 was about 200 square kilometers and expanded afterwards. For the first month of drifting, I'm showing this map again to the top right, where we have this raft going towards the southwest, and it's summarized here in this case. And after that, the raft actually climbed up to the north, and in mid to late August and early September, it's drifted mostly towards the west and reached Lakeba Island here in early September. Satellite imagery is a very efficient tool to monitor where the pumice raft is going, but you need oceanographic simulation to understand, to forecast the dispersal of this pumice raft. And so in this model here, we used combined surface, ocean current, wind and Stokes drift that are summarized here as forces in this little diagram representing an iceberg for pumice. And those three forces could be combined into a single model. And we use the common model that is used for other purposes as well. So we could predict the dispersal of the raft, and we can also use the satellite images such as this one here in dark red for the thick raft and light red for the thin raft, and show that we have ocean currents that swirled and train the raft into this big swirl as well. And in some cases, we have the wind that is acting more on the raft. I'm showing two types of ocean simulations, one short-term at 1 month at the top row, where the satellite data with those dark rim dots show very good match with our model, that is the rainbow colors here. And we just vary the Windage and Stokes drift in those two models, but it works very well. We also have a hindcast model based on data from the past years. And this data shows that not where the raft went, but where it can potentially go. And see that the shores of Australia would be reached in about a year time on this model, which matches what happened in the case of our raft. Using all this data, we managed to release bi-weekly hazard maps that had a forecast for the next 4 days. And we sent this map to the Rescue and Cooperation Center in New Zealand, but also to yachting, shipping and fishing communities in Tonga and Fiji, through social media as well, and word of mouth using key individuals in those islands. So I'm showing here the data from the 13th, 17th September, arriving towards Fiji, and we have the position of the current raft in here in light blue, and in red that's the forecasted dispersal of the raft for the next 4 days. Same here for the 19th to 22nd of September. We have this original red patch that corresponds to the current raft, and also it also matches the previous forecast. And in yellow we have the next forecast. And in both cases, those forecasts work really well, and we could forecast that the capital of Fiji, Suva, would not be hit by the pumice raft, which was very fortunate. So we could forecast the dispersal of this pumice raft, and we could do it in the future based on satellite images, oceanographic models, and regional weather forecasts. Considering that most of the world cargo is transported by sea, we need to better understand those pumice raft and how they can be forecasted, considering they can reach harbors or island states and having major consequences for the sea trade. Thank you.